Welcome to the next session on advanced algorithms. As always, let's look back at what we did last time. Last time we briefly started with depth-bounded search trees, which I call depth-bounded exhaustive search to not cause any confusion with binary search trees, which is something entirely different. We've seen one concrete and simple example. That was an algorithm for vertex cover. A simple one where we consider for each edge, for one edge, we consider the two possibilities that we include one or the other endpoint. And before we go on with that, let me add a topic that's actually overdue for a few sessions. That's namely extending our glossary of problem types. We started that in the first chapter, where we talked about P and NP, and now for the parameterized problems, I wasn't very rigorous in defining what the other types of problems are. We've talked a lot about the decision problems. I think now that we are starting with the algorithms, it's time to be specific what the problem actually is about. So, we've already had two extensions or two slides on problem types. So that's the third. What we had was the, say, classic problems to distinguish them from parameterized problems. So I had the decision problems up here, which was, so these only have a yes-no answer or a threshold in a sense, so a single value that decides. And then here we had the answer is a single thing. And in the bottom row we had the answer is a candidate or a witness for the specific solution. So this was for optimization problems. We usually start with these in applications. That's where we want to find the best solution for a certain problem. And that solution has a quality, a cost. If you only compute the cost of the best solution, it's the evaluation problem. And then for discussing the complexity of problems, it was often easier to go to the left column, where you had the decision problems that you know by now fairly well. And the search problems was given a threshold and just asked for, is there a solution which is better than this threshold? And if so, you should also find a witness for that. So that's the classic world. Now I enjoy the features of the tablets here to make a bit more room. In the parameterized world, I think the best way to view it is that we have a completely new plane and a copy of each of these. So every version of these problems can also have a parameterized version. Okay, very nice. So we have a new plane down here. That's the parameterized problems. I should probably tell you what I mean by a parameterized optimization problem. So we've talked about parameterized decision problems. That was, if we start with an optimization problem and we take the canonical parameterization, then we're given an instance of the decision problem, which naturally involved a threshold. And then the parameterized version was essentially the same question. Is there a solution to this problem where the threshold is given? And we were looking for a solution that's better than the threshold. And we essentially only allowed a different running time bound. So we replaced the polynomial time by FPT type of bound, so the f of k, p of n, it's from the last sessions. For optimization problems, it's maybe not so clear what actually is the problem. So, okay, before... So the decision problems are used to study the complexity of a problem. And in particular, we were interested in lower bounds, if you like, which was showing hardness, right, by reductions. So hardness results are nothing else than lower bounds that are not explicit in terms of some running time function, but essentially not much better than a certain other problem. It's just a relative lower bound. And we continued like this for the parameterized problems. But for the algorithms, also in the classic world, we noted that we can often go down here again and solve the optimization problem by essentially the same ideas. And that's important because we would like to solve these in practice, but study these in theory. But usually that's not a problem. Now in the parameterized world, we should at least think about that another time before we continue with only studying decision problems. So what's a parameterized optimization problem? So for me, the way I would like to understand it here is that we're given an instance for the ordinary optimization problem. Now this instance does not involve some kind of threshold. It's not like here's a graph and an integer k telling what the vertex cover is. So you only get the graph and you're asked to find a minimal vertex cover. So you're not told by the input of the instance what the threshold is that you should look for in the original optimization problem. But in the parameterized world, we can't do anything without a parameter. And we can't take just the value of the optimal solution because the parameter has to be efficiently computable. So that doesn't make sense, okay? Also, it would be requiring the problem to be solved. To solve it would be not very helpful. So in that sense, we require an additional input here, and that's just the parameter value. But unlike for the decision problem where it was naturally part of the input, we now have it additionally. And what's the goal then for the parameterized optimization problems? You find an optimal solution, big surprise, but only if there is one that's better than the parameter threshold. Than the one that you're given. So if you think, okay, we'll discuss it with respect to the example of vertex cover in a second anyway. And if you find out that this is not possible, you can't just reject and say no because we don't have a decision problem. So let's call the action abort. You abort your search. So you can guarantee that there's no solution better than this, but you don't further try to find the actual optimal solution. Okay. Now in the classic world, we always found that going up or going left is essentially easy. That only makes the problem less demanding. You can compute the value of optimal solutions. That's something we assumed for our optimization problems. And of course, you can check whether a given value is below or above a threshold. In the parameterized world, we can, to a good extent, also do that. A bit more space. So we will continue to use decision problems to study complexity. And we will also, to a certain extent, continue with the decision problems to study algorithms. And just like before, going from the top row to the bottom row is usually not hard. So if you're given a specific problem, as you saw in the first exercise sheet, you can usually use a decider for the upper problem as a black box and solve the lower problem by just some polynomially bounded number of calls to that. So any algorithmic solutions for the top row essentially work for the bottom row. And for this direction, you can also use the same idea. You can also use some kind of binary search to find, by threshold questions, certain number of threshold questions, you can find the optimal value. We'll see in a second that in some instances, the binary search here is not the most clever thing you can do. Sometimes you can exploit the parameterized setting a bit. But you don't have to. I mean, in terms of just translating the algorithms, the same ideas work. And this is already good news. And the reason why this is relatively easy is that you can just keep the parameter. So if we define the optimization problems, the parameterized optimization problem like here, that we have this option to abort if there is no solution that's worse than the threshold, than the parameter. Then we can translate between these essentially as before. So let's go back to vertex cover. And I thought it would be helpful to have the algorithm a bit more in detail. Last time I was a bit sketchy, and also I didn't specify the problem very properly. Now here we're looking at vertex cover, which is the optimization problem, and we're looking at the parameterized version of it. So it's exactly the new thing that I just talked about. So we are given a graph and a threshold, but we would like to have an optimal vertex cover, and not only a yes/no as an answer. But the not possible answers that you see here essentially should say not possible with k vertices. So it's a conditional not possible, but since the user inputs the k, he or she is able to interpret. The algorithm is as we've seen before, but I've written it down as a recursive function because there's a few points we might otherwise overlook, I think. So the first thing is here we choose an arbitrary edge of the graph, and then essentially do the two branchings. You either take one endpoint into the solution or the other. So both partial solutions are possible. And to continue, you delete that node from the graph and all edges that would otherwise be dangling. So this construction will appear a few times in the future, and it's always the same. Maybe it would be easier to introduce a notion for deleting nodes from a graph, but it's also not so much of a hassle, so I just wrote it down. We do that for the two nodes, and otherwise, so in completely symmetric ways. Then you recursively solve the instance where you subtract one from the parameter, because we're only interested in vertex covers where we can add that node that we just selected and are still better than the bound. Well, and then the rest is just making sense of what you get back. If there's no possibility for the two, then the whole problem is not possible. If there's one, then you can only return the one. And if you get two different solutions, you can just return the better one. That's a lot of cases to write down, but not anything complicated. So one interesting fact to note here is that the code at no point has to explicitly check whether the candidate solution that he checks that he computes is really a solution of the problem. There's no line like check whether this set of nodes is a vertex cover. That's a bit different from the brute force method for SAT that we discussed, where you just in the first step, guess an assignment and then you check whether it fulfills the formula. If you do that in such a recursive fashion, at least for the vertex cover problem, you don't even have to do this check at one specific point, but just by reducing the graph appropriately, you make sure that it's a solution. And that's why the running time is essentially the exponential part plus something that depends on the graph size, because this edge can be chosen in constant time because we can just pick the first one that we encounter. And then for all these nodes and edges that we remove here, we will only remove them once, but in different paths. I think this is bogus. Forget about it. It's times. You cannot guarantee that you won't remove it several times in different branches of the tree. But nevertheless, it's an FPT algorithm for the parameterized decision version. That's how we wrote it down here. But it also computes an optimal vertex cover if it's a yes instance for the decision problem. And another interesting feature of this very simple method is that the k is only used at one specific point, namely here, where you abort a certain case. But if you happen not to know the k up front, you could still use the same algorithm. If you're a bit careful, so if you replace these recursive calls by, say, a queue of instances that you still have to expand and check, then what happens is that you generate the partial solutions sorted by their cardinality. You add nodes one at a time, and then in the queue you always have solutions of roughly the same size, right? So this will need excessive amounts of memory, but who cares? So in terms of only the running time, we can make sure that we expand the solutions in a breadth-first fashion, and then whenever we hit the first solution of a certain size, we can abort the rest. And that means if we delete that line here, we essentially have an algorithm that solves the ordinary optimization version of vertex cover, but still offers such a runtime guarantee, where now k is actually the size of the optimal vertex cover. Of course, for any given instance, before it has finished, we don't know what the k is, so it's hard to prove any interesting guarantees for any instance you're given. But if you know that your input must consist of graphs that have small vertex covers, you can just run the algorithm without trying to guess a good k. But this is actually something we can always do. Because if you look again at so this was this direction, in a sense, going from the decision problem to the evaluation problem is the essential step that we took here. For the decision problem, we naturally had a parameter or a threshold Whereas for the evaluation problem, it was a free search in a sense. And it would be pretty helpful if we wouldn't have to guess such a parameter up front. And in many cases, we don't have to. If we replace the binary search that we used beforehand by something, so I call it galloping search because it's a vivid term. I think it's also called exponential search. It's a very simple idea. Instead of, so binary search would be always cutting in half and then locating some point in a certain interval. Whereas galloping search starts here and first always doubles the distance, and then when it found a value that's too large, it goes back by binary search and finishes off the search. Okay? I think you can imagine what that looks like. Well, why should that help? So let's assume, like in the vertex cover case, we have a minimization problem. And we have an FPT algorithm for the decision version. Then what we can do is start with small parameters and then make the parameters larger. And since we're in the decision problem, the parameter and the threshold for the decision problem are just the same. But because it's an FPT algorithm, it means that the exponential part will, at least in the beginning, be very small. Okay? And you can exploit that. So this algorithm will have the usual running time. And if you start with small k, that's just potentially much better. And you never have to insert a larger k than twice the actual value of the optimal solution. Right? That's the point where you overshoot the actual solution and can start going back. So in a sense, you can always find such an algorithm for the optimization problem, even if you don't specify the threshold, where to truncate the search. And if you have a maximization problem, you can start from the other end. So this is, this is just kind of a nice general method, which also means that we don't have to worry about always solving the optimization problem. We can essentially stick to the left column. Nevertheless, for many algorithms, it's so easy to just specify the solution and we'll just do it, because such a black box trick is usually slower than a handcrafted method. Okay, so far for the general comments. Let's see one more example of a depth-bounded search that is a tiny bit more interesting than the one for vertex cover. So you recall the problem independent set. We've seen it a few times. Just to repeat once more, you're given a graph, and you ask for a subset of the vertices so that they have no edges in between. These are independent sets. If you parameterize by this threshold, so we're again considering the decision problem, as we've just seen, this is generally sufficient. So the decision version here is W1 hard. We've seen that second to last session. So we won't find an FPT algorithm for that problem, but if we restrict it to planar graphs, there's an FPT solution. So the problem is the same, just that we restrict the graph to be planar. In a second, I'll discuss briefly what planar graphs are. You probably have a picture in mind, but we need a few elementary properties of these. The problem is still NP complete. So going to planar graphs doesn't make the problem trivial. But it's in FPT, as we will see. So this is one instance of a problem where the parameterized theory helps improve the picture is more fine-grained, and where you can exploit that. So we'll see that it's in FPT and can be solved in such a running time, which is maybe still a bit high, but we'll see worse later. Always think that k is small. Okay, to prove that and to give an algorithm for that, we need a bit on planar graphs, a few elementary properties. So, because I'm not sure whether everyone has seen a definition even for planar graphs, let's just briefly discuss an example. That's neither 2 nor 3. So, a graph is planar if there is an embedding of the graph into the plane. So an assignment of coordinates to the nodes so that you can draw all edges without crossings. We'll have to count edges and nodes in a second, and also faces. That's why I give a slightly larger example. So let's also number the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think 11 should be what we have. Okay, maybe another color. So counting vertices in edges is the usual thing. But in planar graphs, we have, because the edges are non-crossing, the edges divide the plane. I'm talking about R2, the Euclidean plane, just as you can see it here. It divides this plane into certain regions, and these are called faces. So in this case, we have 3 interior faces, and then we have, don't forget this one, all the rest. So we have 4 faces. And then there's a famous and just a property of planar graphs that if you count the number of nodes, subtract the number of edges, and add the number of faces, this should always be 2, at least if that thing is connected. So in our case, we have 9 nodes, 11 edges, and 4 faces. And that checks out. The fact is simple enough that we can just briefly prove it. Maybe you've seen that before, but it's so intuitive that you can just remember that if you've not seen it before. So the first case where it's simple, so what's the most simple connected planar graph? The simplest graphs that are connected are trees, right? So it's an undirected graph, so a tree is just something like this without any order on the edges and no roots or something, just some acyclic graph. Now because it's acyclic, it doesn't divide the plane into some more faces. There's no, any face that's not the exterior face needs to have a cycle. That's just proof by a geometric intuition. I haven't defined faces formally anyway. So here we always have, this is more like you should have an intuition why this is true, because I always forget whether this is 2 or some other number, but it's easy to compute that if you know the trees. So trees always have one face, and you know that we always have one more node than edges, because every node can just grab one, and then there's one left. That's essentially, what we've seen many times in introductory algorithms classes. Now, if G is not a tree, but a connected planar graph, then there's certainly some cycle. Otherwise, it would be a tree. In general, this can be part of a larger structure, whatever. But there's one edge that we can cut. So, for example, this one. We just pick any of the cycles, and you pick any of the edges in that cycle. And if you cut that edge, it means that two formally separated regions join into one face. So we get minus 1 on the faces if we remove that edge. And we get a minus 1 on the edges, but the nodes don't change. So that means this term on the left-hand side just remains constant. And if you continue doing that, at some point all the cycles will be gone and you'll be left with a tree. So that's the reverse direction of a proper inductive proof. How many edges do I have to cut till I reach a tree? And then this formula is nice, but for algorithms we usually don't want to enforce connectedness, but it gives a nice upper bound if we drop that. We can show that the edges are bounded by a linear number of in terms of the nodes. We can also prove that because that's another small intuition. We distinguish the case of trees because there the math doesn't check out if for the general argument, but we actually know that this bound holds for trees because we know that there's at most so many edges in a tree, so n minus 1, and this is certainly not more than that. So trees are fine. The more interesting case is that we do have some cycle, and then we use that also we have at least 3 nodes, which is maybe not even a requirement in that case, so this follows. And then any face that we have must be enclosed by at least 3 edges. Otherwise, it just won't get a cycle in the undirected sense. So it could be more, but at least 3 per face. And if we just sum up the edges over all the faces, then we sum up over all faces the edges that limit the face, so sloppy notation. Then we're counting faces twice, we're counting edges twice, but never more than twice, okay? Because here usually will be another face, then we count the edge twice. We might also have such a dangling node that just whose edge doesn't divide the region into 2 faces, but it's just enclosed by a larger face. So if we count 3 edges for each face, double count the edges each at most twice, and then by the formula here, you can insert. Okay, it's not an equal if it's not connected, so it's also an inequality, and then you can just compute that this is the bound on the edges that you get. Sorry, I forgot the 3m. And then subtract and rearrange. Okay, so that's a very simple computation. Now this means we have essentially less than 3n edges. The average degree of a node is just count all edges and divide by the number of nodes. where's the 2 coming from? Because each edge connects to 2 nodes, of course. So the average degree would be at most twice 2m over n. And since m is strictly less than 3n, the average degree is strictly less than 6n. 6, no n. And then from this, we use a very simple form of something that's called Probabilistic Method, which is a fancy name for simply saying if the average is less than 6, there's one node with degree less than 6, so 5 or less. I mean, the proof is very simple. If there wasn't, then we could write the sum that defines the average, use the inequality all greater 6, and then we had an equality by linearity that the average is greater or equal 6, which is a contradiction. I think I don't have to do that. The same, so it's called probabilistic method because instead of average, you can use expectations. That's a trivial observation. Under this name, there's also kindly some more sophisticated versions of this method. And I think we'll see that later in the course. But for the moment, all we need essentially is this. If we have a planar graph, then we always find a node that has degree at most 5. And that's where we can turn into an algorithm. We're given a graph and our truncation threshold k. Now the essence of the algorithm is if G is planar, so we assume G is planar, then we will find one node with minimal degree so that it only has 5 or less neighbors. Now for an independent set, so say this is our node V and it has a few neighbors. There might be, of course, many more edges. Whatever. If we only look at this substructure, any independent set that's supposed to be an optimal one, so a maximal one, has to contain one of these nodes. If it contains none of these 4, then we can include V for sure and still have an independent set. Well, and that's essentially it. So any independent set that's maximal has to contain one of these 5 nodes in that case, and it could be one more. That's the largest degree that we can have. So we just take these 6 or less nodes, and for each of the cases, for each of these nodes, add the node to the solution, and then remove the node and all its neighbors. So if I choose that this one should be in the independent set, then these 2 nodes can be deleted from the solution together with all their edges because I can't pick any of these neighboring nodes in an independent set. And then I recursively check for all 6 or less possibilities whether I can find an independent set with that size at least. And I always included one node, so I always make the parameter 1 smaller. And then in the end, take the best one of these. So this is finally the algorithm that's going to have this time and yield a proof to this claim. We should show that it's correct and has the proper time bound. Oh, why is that again the end of the slides? Okay. Let's briefly restate why this algorithm always finds an independent set of at least k nodes if there is one. So any maximal independent set has to contain one node from, let me just do it like this, from this set. That's what I argued in the picture. And here we need a slightly stronger argument. For the vertex cover, it was sufficient to say every edge has to be covered, so already feasibility guaranteed us that the branching is correct. Here we need also maximality. So if the solution wasn't required to be optimal, maybe that wouldn't work, but any optimal independent set has to contain one of these nodes. So we'll never miss a maximal solution. Okay, that's fine for a maximization problem. And we check all possibilities of these. I just abbreviate that a bit. Now, what's the size of the search space? Well, in every step, we do up to 6 different recursive calls. And we always make the parameter smaller by 1. Okay, I didn't talk about the initial conditions, about the determination criteria, but simple enough, I guess. If we are asked to include more nodes in the independent set than there are in the graph, then there's no solution. So this seems like a silly condition, but we will reach it by making the graph smaller eventually. Or the other possibility is that there's just no more edges that could spoil our game, then we can just return the whole graph. So this reduction rule will produce isolated nodes, and I'll just leave them in. You could also already try to delete them from the graph, but it's not really required. So this is again an example of an algorithm that doesn't explicitly check the validity of the solution candidates. It's just by the recursive structure of the rules that we will never generate non-independent sets. Okay. Okay, at most 6 recursive calls. Always make k 1 smaller. So at most 6 to the k different solutions that we try. And then what remains is essentially this step number 4, where we have to find a node of minimal degree. That's some linear time operation, right? So line 4 is linear time in the graph. Okay, doing it in time O of n would require a good representation of the edges. Maybe replace n by m, whatever. With a good data structure where you count the edges, count the degrees already, you can do. Okay, I'm still fighting with the unfeature of Xornal to cleverly detect that a PDF has a certain number of pages and then just stop. Even if you replace the PDF then afterwards, it's clever enough to stop at that certain page that was the last one before. So that's where we've been. Now everything I've written has gone. And let me briefly save that it's not lost. So we've seen 2 simple examples where it was very easy to just count the number of different solutions that we have to look at. In general, it can be a bit more interesting. We'll see another example in a second. You know what, let me just do the example first, and then we'll do the math. So I prepared some slides down here. Let's look at another algorithm for vertex cover. So you might, at some point in time you might want to see a different problem, but here's vertex cover again. So we've seen the 2 to the k search space size. And we can do better significantly by essentially a very simple trick. So why this wicked numbers show up, you will see in a second. And there's nothing magically behind that. That's just the root of a cubic polynomial. And these turn out to be, you know, non-elementary or usually you need at least cubic roots. Okay. The idea is how you would prove this theorem. We make more case distinctions. If the graph that we are given has only degrees 0, 1, and 2, so the maximum degree is 2, how does such a graph look like? Okay, it can have isolated vertices. Boring. It can have vertices of degree 1, and you can build paths, and you can stop. Or you can build cycles. And that's it. You can't even join the path and the circle. That would already make a degree 3 vertex at least. And you can't have junctions. So these graphs are very, very harmless. And you can immediately construct an optimal vertex cover for these. So you ignore all isolated vertices. In the cycles, you pick every other node, so many as you have to cover all edges. And in the paths, you pick every other node. The only important thing is you should not start with the first node. That would be stupid. But everything else is giving you an optimal vertex cover. So these are essentially trivial. So you decompose into connected components and then start with the degree 1 vertices if you have one, and then pick every other node. So that's linear time, essentially. So if our graph happens to be of this very specific form, we won't have a very hard life in finding the vertex cover. Usually it will not. But if it is not of this form, then we can use the mother of all vertex cover reduction rules. For every vertex, we either have to include this vertex or all its neighbors, because we have to cover the edges incident to that vertex V. The good thing now, if we exclude this case 1, is now we know there's a vertex of degree at least 3, like the one I've just drawn. And we only ever apply this rule 2 now to such high degree vertices. And that's essentially the algorithm. So of course, you should write it down like before. You can simply set up a similar recursive method. Now the two possibilities here, the two branching things, are not symmetric anymore, because for one part you choose one vertex, and for the other you reduce the parameter by 3, because you have to include all 3 in the solution, right? So it's the same structure of the algorithm. But if you analyze the search space, well, just to reiterate, in case number 1, we don't have any recursive calls. We just solve that to optimality. We only have recursive calls if there is a node of that degree. So if we say tk is the size of the search space that we have to consider when the parameter is k. What I mean by size of search space is the leaves of the recursive calls. So the intermediate steps where you still go on with branching are not so interesting, because the final candidates for solutions the leaves down at the tree. Well, and you can probably cook up a worst case instance where you have to go all the way down before you can prune any branches. And the second argument is we only have binary nodes, so the number of leaves is larger than the number of interior nodes. So we only miss a factor of 2 if you ignore the interior nodes, if you like. So if we have that size, then we can set up a recurrence. And so assuming we're in this case too, we have the size where we have only v in, and we have the size where we have the neighbors in. Well, essentially, this is a less or equal. We don't know what the actual degree of this vertex is. It could be larger than 3. And in fact, we can just pick here. So we have to select some vertex of degree at least 3. We can always pick the one with a maximal degree. That's, I mean, it's a good heuristic. It would probably always be better than just picking any one. So that is just upper bounded like this. Well, and that's a recurrence where you can just explicitly say, okay, that's a magic number to the k. But as you saw in the statement of a theorem, there is one such number, so that essentially, in the O term at least, it's number to the k. And we'll compute that number in the general setting. And the good thing is that this is something that's mathematically easy to study. It's a linear recurrence with constant coefficients. For which we can use generating functions. Of course, there can't be a lecture from our group where no generating functions occur at some point in time. And here it didn't even require making any excursions or whatever, so it naturally arises in that setting. But I will go over it a bit more quickly because you have already seen that. I'll still do it in a bit of a detail. So assume you're given such a branching vector. So in our case, we had 1 and 3. So this vector, which is just the size in which the parameter is reduced in the different branches that we consider recursively. And we had 1 node and 3 node that are subtracted. Then in general, you have a recurrence of this shape. For all these depth-bounded search tree thingies, you will have a recurrence of this shape. And then you can explicitly solve that. So this is an equal, not even asymptotics required. And these terms are maybe a bit unwieldy, but the important part is there's a constant to the n. And the rest is polynomial and then some linear combination of these. I'll talk about the corollary in a second. So these z's are just the roots of a certain polynomial that depends on this vector. So in our case, that would be c to the 3, c to the 1, and minus 2, minus 1. So the last term is always 1. And the roots of this thing is something you'll just have to compute, but numerically it's always easy to do. And that gives you the CL. Now these roots could be multiple roots, and in that case you also get a polynomial factor. For our applications, we will never encounter multiple roots that are dominant, and we will always have real roots. That's even something you can prove that in our case you can't have imaginary roots that are dominant. What I mean by dominant is a root of largest absolute value, which in our case then will be this 1.4 and so I forgot. And if you insert all the other roots, then the other roots are strictly smaller. So you have an exponential distance between the largest one and the others. And if in case of multiple roots, then you have a polynomial. So it's at least an n factor that's missing from the leading term. And so without any further restrictions, if D is the size of this vector, then you always have a form of this shape. But you could actually replace the D by the multiplicity of the dominant root, if you like. Okay, let me see where I have the computations over here. I certainly want to give you an idea why this is the solution, but maybe not in all the details. That someone would require who sees it for the very first time. So we had this recurrence, n minus di. And I'll just write d for the maximal entry of this vector. That makes the formulas a bit nicer. Now we're considering generating functions, which is just some power series in a formal sense. So for this part of the theory, you're not even required to think about convergence issues of these series. You can essentially treat them as formal algebraic objects, but we won't need that here at all. In our case, there will always be some ball around zero where these things are absolutely convergent. For this lecture, just use this as a magic tool that transforms a sequence of numbers into a function of a real or complex variable, and allows to use some computational tricks. That's essentially what we'll do. So if you insert our recurrence, there's we have to split up a few terms. This sum starts at 0, but our recursive form is only valid for large enough n so that these make sense. So I think I didn't state initial conditions, so we assume that t0 up to td minus 1 are just some numbers. And depending on these numbers, we will have some coefficients here, but the order of growth will not depend on the initial conditions. Unless these c's turn out to be 0, which they will not if these are all just positive and real numbers. So let's just keep them formally here as some constants that we don't care too much. And then the sum starts at d. And for these t's, we can use the recursive representation. And now we split the sums and shift indices. So these will just keep. And let me write this as a sum over the indices of this vector. Then we can pull out a certain number of c's. So we would like to make these sums of the same form that we have for the generating function. That's why I take a few of the c's and pull them out of the sum. Now we're almost there. The only problem is that we start a bit too late. where we can just add and subtract the terms that are missing. So here we have, again, the same form as here. After shifting this down, and how many do we have? Okay. Okay, I have to insert. For the largest, we don't have any term. Another -1, hopefully. You should double check. Well, it's a finite sum that depends only on this branching parameter. I could have, well, okay, I can write it with dot, 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 if you like that better.
Oh, okay.
It's because of, it's the transformation of this sum. This turned into this sum. I exchanged the order of summation, which is fine because the sums are convergent.
Wouldn't it have to be z to the d instead of?
At which point?
Well, just right there. Those both sums, shouldn't they be z to the d instead of?
So d was the maximal entry of this vector, and here we pull out just as many as we have here. So the good thing, even though it's in the general form a bit unwieldy maybe, we can split these two sums, the one with the t of c and the other one where that is essentially just some polynomial. And then we can move all the t of c's to the other side. Is that clear? And then we can, okay, maybe one more step, okay. You have the t of c, then we have minus this sum. And what remains on this side is essentially the same as before. And these here. And now we can extract the t and divide. So it's this nice term. Let's give it a name so that I don't have to copy it again. And observe that this a is some polynomial in C with degree d minus 1. The exact representation is not so nice, but it only depends on the initial values of the recurrence. And here we have 1 minus and this sum. And this is essentially the characteristic polynomial, but we have c to the d pulled out, essentially. So the characteristic polynomial was c to the d minus c to the d minus d1 and so on. And that's exactly this here if you divide by z to the d. So this denominator is this. So you see that we're approaching something that we know. But why is this at all helpful? At some point in time, we have to go back from this world of generating functions, of the world of series, to the actual series that we're interested in. But the good thing here is that the generating function turned out to be a rational function. It's a quotient of two polynomials. And these can always be written in a specific form, which is called partial fraction decomposition. So in this very general form, it again looks a bit frightening. But for the specific terms that one usually encounters, it's a simple thing to do. So partial fraction decomposition means that we have a large sum of terms instead of a large fraction. And we have to factor the polynomial down here to see its roots. And then if the roots are multiple, then you have a sequence of sums like this, where you have to increase the power here. And the a's are just some fixed numbers, some fixed constants that you have to compute, or that you are guaranteed that they exist, and you can compute them if you need them. So that's terms for, okay, let's call the denominator b. And usually this will have more than one root. Then you will have more of these sums. They're all of the same form. And so on. So the general form is not so nice. But all that we need here is that it exists. There's some form that only consists of terms constant divided by something of this specific form, maybe with a power. So z1 another root. Well, why are these terms of particular nice forms? Because they are essentially the generalized geometric series or powers thereof, which means derivatives. So the simplest form, okay, I mixed it up. The simplest form of this formula is this one. If you sum up all powers of c, then at least for c less than 1, you can write it in terms of this. And if you take derivatives on both sides, then you get representations as series for these general summands that we have in our partial fraction decomposition. And then by simply equating coefficients, you can subtract the solution for our recurrence. Since we don't have just c to the don't have just these terms, but also divide by z0, we just have to make a change of variables, and then we'll have a z divided by z0 to the n, which is z0 to the minus n. Then these general terms have a polynomial factor, which in general should be something like following factorials, but and so on and so forth. So the interesting thing here is we have exponential parts, and then only these n's, and the rest is constants. So for one, this is exactly the form that we claimed in the theorem. So this proves the theorem, and these constants that we have here depend on the initial conditions. And for the corollary that I also listed, you only have to note that if there's a different root that has a smaller absolute value, then it's exponentially smaller than all the other terms. And among all terms from one root, certainly the one with the highest power at n is the dominant one. So that's a relatively simple way to find the leading term coefficient, or the leading term asymptotic. Okay, yeah, some of you are smiling. You know that there's much more mathematical machinery behind this. Maybe we'll look next time a bit into generalizations. If here we have some inhomogeneous part, some other sequence depending on n. If this is a specific simple polynomial or an exponential, for certain specific functions, it's relatively easy to still do the same tricks. And for a certain large regime of series here, you can show asymptotic transfers that we might require in a certain restricted form in 1 or 2 sessions. So for the vertex cover example, we had this, and we should factor this polynomial, which then already had, so this is one thing that I didn't mention. Here we have the roots here are with a negative power, because we multiply by c to the d to get from one to the other. We get, we can write this as a transformation of the variable. And then you get a 1 over for the roots. Maybe we'll skip that. I haven't written down the details for this last step. It's okay, it's simply by inserting. That's boring enough. Okay. So in this example, for the vertex cover algorithm, we had only one case and then 2 different branches with different sizes. In more wicked algorithms, we might also have more case distinctions than we had. So for the vertex cover, we had one trivial case where we could stop immediately, and one case where we branched in these 2, 1 smaller, 3 smaller subproblems. In the general case, you can have different rules that have different branching vectors. And then a simple argument would be you compute the search size for every rule in isolation and then just take the largest one. That will certainly give you an upper bound. Okay. Now I would like to leave the vertex cover problem. Okay, here it is again. And come to an entirely different problem. So no graphs at this point, a very different problem, but one where we also can apply our machinery. And the algorithm has a slightly different flavor. So I think it's a good example to also see the wealth of FPT algorithms. I forgot to show you that I also wrote down the vertex cover algorithm for these 2 simple rules that we just had. But you see there's a lot of prose in between. So this is my algorithm for finding the optimal vertex cover in the max degree 2 graphs, which is pick every other node. It's a bit sketchy, but it would be easy to fill out the details. I just wrote it down to show you that the rest is essentially like before, just that we now have two different branches, which is shown that now the set of vertices to be deleted in the graph or to be added to the vertex cover, that's the same, is one node or all its neighbors, and that's why we have a different reduction in the sizes. Apart from that, the algorithm is very much like the one before, and I think I don't discuss it in further detail. Okay, as promised, no graphs for the moment anymore. We'll just have time to discuss the problem a bit, and then next time we'll show the wicked algorithm to solve it. It's not so wicked after all, but also not so fast after all. You'll see. So we have a sequence of strings, m strings, and they are all of the same length. And this is an important restriction here. Over some alphabet, and we're also given a number, so we consider the decision problem. And the parameter is also this k again. And we're looking for a string that's close to all of the strings in the input. So it's like it says the closest string. Since it's a decision problem, we ask for, is there a string that has at most k mismatches to any of the other strings? So dh is the Hamming distance, which is just the number of positions where the two strings have a mismatch. And since these are all of the same length, so the Hamming distance is simply the sum over each position. So you compare each position, is the letter at that position the same in the strings or not, and you count the number of positions where they are different. So you should add that in practice, a problem that people are more interested in is actually that these strings are maybe not necessarily all of the same length, and that also this consensus string is not necessarily of the same length, which means that you have to find a different metric of string distance, and that makes the problem a lot more complicated. And for some formalization of this more general problem, we can show that in terms of the distance you allow, it's W1 hard, which is bad news. So you probably can't solve it for the general case when the sizes don't match. But here for the Hamming distance, you can exploit a bit more of the structure because all the columns are independent. This is what we will exploit in the algorithm. And for that problem, we'll see that it's in FPT. And we'll devise an algorithm for that. We can maybe start with a very simple lemma. Since all these strings are of the same length, we can write them just below each other. And that gives us a matrix of symbols. And in these matrices, we can look at the columns. And we call the column dirty if there's not all the same symbols. Certainly, the dirty columns are the only ones that make us headaches. For the others, we just copy that symbol into the consensus string. And now you can imagine if there's too many dirty columns, you will not find a solution. And a very simple bound is this. If you allow a distance of k mismatches between the consensus and all the input strings, then if you have more than m times k dirty columns, you're out of luck. And the reason is a simple pigeonhole principle. So if you have strictly more than m times k columns and m strings, there must be one string that has more than its share. That means more than k mismatched columns. And essentially this makes it impossible to find such a string. So this is, okay, maybe it was a bit sketchy. So for any consensus string that you pick, no matter which one it is, it has mismatches in m times k columns because it can only take one of the symbols in that column. And then for any fixed consensus string, there is one of the strings that has m plus 1 mismatches. So it's not the same input string for all consensus strings, but for every consensus string there must be one, because there's just too many dirty columns to distribute them across all the strings. Sorry. Yeah, of course. Okay, that was your confusion? Yeah, it's k plus 1. I just copied it the wrong way. So the idea is you divide something that's larger than this by m, and then something larger than k remains. Okay. Yeah, I think we'll look at the algorithm next time. We'll need one more simple lemma, and then the algorithm essentially is relatively straightforward. But again, there's a few tricks to combine so that you show the running time in the end. More on that next time.